Welcome. My name is Clayton. I'm one of the tutors in the Natural Sciences Tutoring Center at SCC. Today we're going to be talking about vectors. This will be a two-part video. The first part will be on some of the more fundamental vectors. The second one will be on more advanced vectors. So why don't we just go ahead and get started. We have a question right here. I'm going to have it at the bottom of the screen as well, in case you can't read my handwriting, which is very likely. I'm going to go ahead and read it here. From his house, John walks 5 miles north, 3 miles west, and then 2 miles south. What is his displacement? So a couple things here to break down. First of all, we got to talk about what a vector even is, right? A vector is any quantity that has both magnitude and directions. So in this question, we can pull out the vectors right away here. First one I see is 5 miles north. So the magnitude is 5 miles. The direction is north. If we just had 5 miles and north wasn't on there, this wouldn't be a vector. It would be just some distance. But because we have the magnitude and direction, we have ourselves a vector. So here, 5 miles north, that is a vector. Another one here, 3 miles west. That is another vector. Pull that out. And finally, we have 2 miles south. So let's pull this guy out as I punch my board. Perfect. All right, cool. So now we have our vectors laid out here. And again, what we're talking about is a magnitude and a direction. If I only said 2 miles, that's a distance. That is a scalar quantity, no direction involved. As soon as I slap south on it, or 5 miles north, now we have a vector. And displacement is a vector, while distance is just a scalar quantity. All right, so give me 1 second. I'm going to draw these up on the board here, and we'll be right back. All right, perfect. So what we have here is each of these three vectors drawn out. So 5 miles north is in blue, 3 miles west is red, and 2 miles south is in green. And the way that I've drawn these, this is called tip to tail. So here is the tail of the first vector. Here's the tip. Of your second vector, you just put that right on the tip of the previous one, and then draw, whichever direction, wherever that one's supposed to go. And then the third one, you do the same thing. So this is what it looks like when you're drawing vectors tip to tail. What we want to do here, if we want his final displacement, that's different than the distance. We already kind of talked about that, right? If I want his total distance, that's 5 miles plus 3 miles plus 2 miles. He definitely walked that whole distance. So that's going to be 5, 3, and 2. All right, so that's 10 miles. But we want his displacement. Displacement is where did you start versus where did you end. It doesn't matter how you got there. Displacement is path independent. So whether he walked 10 miles to get there or walked around his entire neighborhood to get there, and it took him, 20 miles, how big is his neighborhood, right? His displacement, if he ends up in this location, is the same. It is path independent. Distance, on the other hand, is path dependent. All right, so the goal here is to get his displacement. All I care about is where did he start, right here, versus where did he end, right here. So I want this distance and direction. All right, so first we're going to get the magnitude. That is the distance between here and here is the magnitude of our vector. And then the angle is going to be our direction. So to get the magnitude of our vector here, we're going to have to break this into x and y components. So we'll say net x equals and net y equals. And that just means all of the x's added together. So this is the sum of the x components and the sum of the y components. So you might also see that like this maybe, if I can draw this epsilon correctly, and sum of the y. So however you are, you learn it or whatever, this is all the same thing. All the x components added together, all the y components added together. I can see that this vector right here has both an x portion, that's right here, it moves to the left this far, that's in the x direction, and it moves up this far, and that is in the y direction. We have a nice little right angle here. So this is the x and this is the y. And what this is the net x in the net y. What I want to do is boil down all three of these vectors into one vector. That vector is called the resultant vector. All right, so now let's go ahead and break each one of these down. I'm going to get rid of these sum ofs because it does mean the same thing as net x and net y. So if you use those, you've seen it here. But again, you use whatever notation you're comfortable with. So we're going to start with the blue one here, 5 miles north. Well, in the x direction, that's 0. All right, 0. In the y direction, 5 miles north. In my world, north or up, I call positive. So I'm going to just call that 5 miles. All right, let's look at the red one. So now we have this 3 miles to the west. Well, this is in the x direction, the x axis here. And so I'm going to say, oh, and again, because this is left, in my personal world, left is negative. So I will say minus 3 miles. Minus. And then there's no y direction, so this is just going to be plus 0. And for our third one here, 2 miles to the south, well, if up is positive, then down must be negative. These directions, and again, that's in the y direction, so that goes over here, minus 2 miles, and there's nothing in the x direction, so plus 0 once again. So we got to really be careful here. If I said plus 2 miles, that would put my resultant vector way up here somewhere. And that is in a much different direction and a much different distance than the minus 2 miles here, okay? These directions really matter, so make sure you're paying close attention to what we're doing there. All right, so we're going to get a total value here. So 0 minus 3 plus 0 equals minus 3 miles. 5 plus 0 minus 2 equals 3 miles. Okay, so I have my net x equals negative 3, and my net y equals positive 3. So I'm going to go ahead and pull this little triangle out right here. This looks like this here. Let's fix that. All right, so we have our x, and that equals negative 3 miles, and our y, and that equals 3 miles. All right, so you may have seen this before. What we're going to do is solve for our resultant. This is our resultant vector. And so we need to use the Pythagorean theorem to solve for this. All right, so as you may remember, that looks like this. A squared plus b squared equals c squared. We didn't use those terms though. We used x, y, and r. So let's go ahead and adjust that. X squared plus y squared equals r squared. All right, so let's go ahead and plug those values in. I got negative 3 miles squared plus 3 miles squared equals r squared. Excuse my sloppy tube up there. Okay. Good. So here we have, all right, negative 3 squared plus 3 squared, that's 18 equals r squared. So square root of 18 equals r, and that equals some number. So give me a second, I'll do a little bit of math here. on my calculator, and we will get a number for that. All right, so the square root of 18 equals 4.24. All right, so our resultant, the magnitude of our resultant vector is 4.24 miles. R equals 4.24 miles. There we go. All right, so let me clear some things off the board here, and then we'll get our direction. So give me a quick second. Right back. Okay, welcome back. All I did was erase our little x-net equations over here. So hopefully you have those. So what we found was the magnitude. Now we need to find the direction. And here's why. If I say that r is 4.24 miles, our resultant vector is 4.24 miles, that means that John is 4.2 miles away from his house. Well, that could be here. That could be also anywhere in that 4.24 radius. That puts John simply some distance from his house. So he could be over here. That's 4.24 miles from his house, right? So now we need to get our directions. Very important, because that will put John exactly in this location rather than any of these others in the perimeter of this circle here. All right, so how do we do that? We are looking for this angle, which we will call theta. We want the angle between, so from here, this would be west, and we're traveling north from west. So I want this angle, and it would be north of west. We could go for this angle. Call it phi, who cares? If I were labeling this angle, we would call that west of north. And that's just, more or less comes down to a little bit of common sense there for how you're describing them. But you do have to describe them. Additionally, because I'm describing it as west or north of west, I'm going to use theta. So I'm going to use this angle right here. I want to keep the angle in the first quadrant. For that reason, I am not going to worry about negatives or positive signs on these values, okay? So what I need to know is what kind of relationship does this angle have with the information that I already know? I know x and I know y. So I'm going to use tangent. I know that tangent of theta equals the opposite side over the adjacent side. Well, in this case, the opposite side, that's y. The adjacent side is x. So that will be y over x. Unfortunately, tangent solves for this ratio, not for our angle. So we're going to use inverse tangent. Inverse tangent of y over x equals theta. So we're just going to, and if you push second tangent on your calculator, that's where this can be found. All right, so theta then equals, let's throw this in the calculator here, inverse tangent, y over x, so that will be, and again, I'm going to use only positive magnitudes here because I intentionally want an angle between 0 and 90. I want an angle that's a first quadrant angle because I'm going to describe it as north of west. So I only want something between 0 and 90. So I'm going to say tangent, or inverse tangent of 3 over 3, and that equals 45 degrees. All right, perfect. All right, so we have 45 degrees, and this is north of west. If I go straight west and then I travel north from there, I will get to whatever this angle is, right? So let's say 45 degrees north of west. And here, I'm just going to note real quick, if we only had the direction, then he could be anywhere along this line. So with just the magnitude, he could be anywhere in this radius. With just a direction, he could be anywhere on this line. And so with only one component of your vector, you have unlimited options. So we have to be very specific in denoting his location at this point. So finally, we have r equals 4.24 miles. And then my personal notation, I just say at 45 degrees north of west. So there is the answer to our question. What is his displacement? 4.24 miles at 45 degrees north of west. All right, so this is one method to do this. I'm going to show you another method real quick, and it's actually the method that I personally prefer. So I'm going to erase the board, and we're going to jump through all that real quick. So give me 1 second again. All right, welcome back. So this method here, I already have drawn my diagram again. And so what you'll notice is I did not use the tip to tail method. I personally am not a huge fan of that method, only because if you ask me to draw a bunch of straight lines and make them accurate, not going to happen. I am not, an artist, or and I don't carry a protractor around with me. So what I like to do is just put all of the tails at the origin. Now, if I add all these up, so it might be harder to visualize where your resultant is going to be doing it like this, and I freely admit that. However, the more vectors you have, so say we had 6 vectors, well, now putting them all tip to tail, if every single one of them isn't to scale, you don't know where you're going to end up, or at least I don't know where I would end up. And so I like to use this method. Each vector, it's the same thing, but visually it's a little different. We're still going to pull out the x and y components of each of these vectors. The only difference is what this looks like. I only want to draw one triangle at the end of the day and then be done with it. And so I'm going to add up my x, add up my y, draw my triangle, get the resultant, get the angle. So you'll see here, it's pretty much the exact same thing. I'm going to go through a little faster here because we don't really need to talk about the same stuff over again. So in the x direction, the blue vector here is 0, 5 miles. Once again, the red one is going to be minus 3 miles. Left is negative for me. 0 in the y direction, and our green one is plus 0 in the x direction, minus 2 miles in the y direction. And once again, here we see, yeah, we're going to get the exact same thing that we already had. So negative 3 miles and positive 3 miles. Alrighty, so now my net x is minus 3. So if I start here, when I draw my resultant, this is my net x and y. So net x minus 3, y is plus 3. So there's that. Plus 3, so this is my y, that's my x. My resultant is this guy right here. That is very poorly drawn. All right, a little better. Anyway, so we need our resultant again. So we'll use Pythagorean's theorem, x squared plus y squared equals r squared. Once again, r is the same thing, square root of 18 equals 4.24 miles. So r equals 4.24 miles. And so from here, you can already see, once we get to this final triangle, just like we had to for the other one using a net x and a net y equation, it's the exact same. So I'm just going to run through this real quick here now, just to show it again. Theta equals, okay, I know that inverse tangent. So there's my r, and we have inverse tangent of opposite over adjacent. And again, I'm going to use only the positive magnitudes because I want an angle in the first quadrant again, because I'm going to describe where the angle is. This is 45 degrees is north of west. So once again, we have our final resultant vector right here, 4.24 miles at 45 degrees north of west. Again, the reason I like this method is because the more vectors you add, it's less complicated just to throw them all on the origin. You don't want to be drawing a whole page full of vectors tip to tail, because then it's a waste of space. You might not draw them to scale. I certainly don't. And next thing you know, you're expecting a resultant vector to be up here, but just because of how it was drawn and it wasn't to scale, the reality is down here. And so now, why did that happen? Well, we just didn't draw to scale, right? So again, that's why I like this method. It kind of simplifies things. One triangle, you're done. But again, they're effectively the same thing. So do what makes the most sense to your brain. That's the most important thing at the end of the day. Okay, so there will be a follow-up video on more advanced vectors, so stay tuned for that. Again, my name is Clayton with the Natural Science Tutoring Center at SCC. Thank you very much for your time. Take care.